All right, welcome back. This is part two. We're going to do a PhET simulation. In a little bit, I'll show you guys how to get onto this PhET simulation so you can do it yourself. But let's talk about how isotopes decay. We've already talked about in the last section about carbon-14 turning into nitrogen-14. If we take a bunch of carbon, so you're taking a bunch of carbon-14, all right, that's radioactive. After one half-life, see how the timeline has got to about half? That'll be about 5,730 years. Half of the carbon-14 should actually go to nitrogen-14. Let's reset those nuclei back to carbon-14, and then we'll redo the simulation. We'll start again. And you can see we'll pause at one half-life. Half of the carbon-14 that was out of the bucket has now turned into nitrogen-14. If we continue letting this go, after about another half-life, which would be a total time of a little over 11,000 years, we should now see that we only have a quarter, or 25% of the carbon-14 is still carbon-14. 75% of it, all the blue, has turned into nitrogen-14, the daughter cell. Carbon-14 is the parent isotope, and then the daughter isotope is the nitrogen. Okay, so this is showing for carbon-14 turned into nitrogen-14. That's one of the isotopes that we use in order to date fossils. If we're not dating fossils, we probably would want to use something like uranium. Uranium is a naturally occurring isotope, and it's a heavy isotope, and it's found in a lot of rocks. So you'll find it in granite deposits, and so it's a good thing to measure the age of rocks, assuming that there is some uranium in there. So if we take some uranium, so get a good supply of uranium here, and then I'm going to go ahead and let the time go. Now, notice this time, the time frame, one half life, is actually measured in billions of years, and it's actually a little over 4 billion years. So, if you start the time process, some of the uranium will turn into lead. Lead is not radioactive, and so it's not going to give off that energy, which is depicted here as the light given off. In real life, you could not see the energy given off by uranium. You'd need a Geiger counter or something to detect it. And so you can continue letting it go. After another half-life, which would be a little over 8 billion years, we'd be down to 75% of the uranium is turned into lead, and only 25% of the uranium is still uranium-238. And you go a little over 12 billion years, and now you should be down to 25%. Sorry, one half-life would be 50, two half-lives would be 25%, three half-lives 12.5%. So we should only have 12.5% of the uranium is still uranium. The parent isotope, the daughter isotope, lead, is what's remaining. So if you actually sampled a rock that had this ratio, you would know that it's gone through 3 half-lives, or a little over 12 billion years, and actually it's more than that. But I'm rounding to a 4 billion half-life time. So you can then use uranium to lead transition in order to figure out the relative age of a rock. The simulation lets you do custom ones. It lets you play with what the half-life is going to be, and this time is actually measured in seconds. So this would be a really unstable nucleus that goes through that radioactive decay fairly fast. So that's the first part of the simulation. It also goes through kind of just to show the graphics that we used in the last. We put a bunch of carbon-14, so carbon-14 is red. When it turns blue, you can see that it's turned into nitrogen-14. In real life, you wouldn't be able to see that. It would actually turn from one element to the other. But you can see how we started off with 100% carbon-14. After one half-life, we're down to 50%. The daughter isotope has gone up to 50%. And then this trend just continues. This trend is true if you do it for carbon or if you do it for uranium. Same pattern. This is going to be true for all radioactive isotopes. All things that have an unstable nucleus will go and do this process. Okay, so we can actually use this to measure how long ago something died, or how long ago it was deposited, or how long ago a rock formed. So let's talk a little bit about the next part, which is measurements. In this simulation, they just use a Geiger counter. Okay, so in this Geiger counter, they say is you can either have it measure carbon-14 or uranium. So you can do things like plant a tree and let that tree grow. If you measure the radioactivity, notice it stays at 100%. 100% of what? Of what the outside air is. So the tree should have the exact same radioactivity as the air, as the ground. Now, they give you the option of killing the tree. What's going to happen when you kill the tree? Well, that means the tree is no longer taking in carbon dioxide. The carbon dioxide was that where it got its carbon-12. And so once trees die, they are no longer absorbing more carbon-14, and therefore the amount of carbon-14 in the tree will actually start to diminish. So let's kill the tree. Sorry, tree. Okay, and notice dead tree. Now if we measure over time, the percentage of carbon-14 is going down, and this is relative to just what it was when it was alive. So I'm going to pause it when it gets to 50%. And pause. Notice it actually was a little bit past one half-life, and that should be because we didn't kill the tree right away. We didn't kill the tree at 0 days. We let it grow for a while, and so it's only from here that it's 5,730 years from the point where it dies do we actually know how long it died. Right? Carbon-14 dating does not do. You cannot date things that are alive because they will always have 100% of the carbon-14. If we continue letting it probe, that dead wood, that dead tree will continue to decrease in its carbon-14. And if we click here, we can actually watch, and I'll reset this, plant a new tree, let it grow for 1,000 years, kill the tree. Okay, notice only after I killed it did the percentage drop, and I thought it was going to show the ratio of carbon. Oh, it is showing, it's just the ratio here. It's showing this kind of the same trend. So you can also then do the simulation with a rock. If you have a volcanic eruption, it shoots up all different types of debris into the space. Well, not space, but space around it. Notice once it solidifies, we can now go and we're not going to use uranium or carbon because notice it's showing no carbon, and I don't expect a rock to have carbon necessarily. Hopefully, though, and most magma will have uranium. Or things that are solidified lava will have some uranium. And so you can actually measure, and so originally it's going to have 100% of the uranium. None of it has actually transferred over to lead. We cool the rock, and we let this play, and we're now doing a time. Notice the amount of uranium is now dropping, just like carbon dropped. And only this time the timeline is way different. Why? Because uranium has a different half-life, right? It's about 4.4 billion years. And so we'll wait, and right, so it's a little bit. So we can now estimate that this rock was ejected, was formed, and cooled about 4.4 billion years ago. And why am I off here? Because it wasn't ejected right away. It didn't eject at time 0. Okay. So anyway, you get the idea. All right, now here's the interactive part of this. I want you to go and do the dating game. Okay, so I'll do a couple examples of how to do the dating game, and you guys will then have to try to date the rest of the things. Okay, so I'll show you how to do it, and then I'll tell you how I want you to submit this to show that you have actually completed the dating game. Okay, so you have the probe. In that probe, you can measure the amount of carbon-14, you can measure the amount of uranium-238, or you can do a custom. So, and the custom allows you to do 4 different time frames. And so you can customize what is a half-life. Is a half-life 100,000 years? Right, K for 1,000. 100,000 years? Is it 1 million years? Is it 10 million years? Or 100 million years? Okay, so there are isotopes that have those, maybe not those exact, but similar half-lives. So let's start doing this. So I'm going to start with carbon-14, and I'm only going to do things that were living, right? Because living things like a tree, right? Notice this says it's 100%, which means the relative age of the tree, I can just say 0. Why? Because I don't know, right? I can't tell the age of living things, and it gives me a little feedback that yes, it hasn't died. So this has died 0 years ago. On the other hand, if I go to the house is made out of wood. It's now at 99.1%, which means that the wood in the house is died some time ago. So we can actually take this bar and move, and all I'm going to do is try to match up that 99.1. We continue closer. Might not be able to get exact, so 99.6, 98.7. So I'm only going to estimate, and then the program will allow for you to estimate. So I know it's going to be older than 52 years, but less than 92. Oh, let's go. So more than 52, right, but less than 92. So yeah, I'm pretty sure if you put anything in between those two, you're going to be able to get the age of this house. So I know it's more than 52, less than 92, so I'm just going to split the difference. I'm going to say 70 years old. Okay, and notice you don't have to be exact. It's not looking for exact. Scientists can give it more exact. You're just looking for the relative age using the percentage of that isotope that still is remaining. Okay. All right, we got a dead tree over here. Right, you can do the same system that I just did. Notice it's a little bit less. It's a smaller percentage, which means it's going to be older than the house. Now let's go and do something like here. No. When you get down to 0.8, that's a little low. So let's do something younger. And if we've already hopefully covered the law of superposition, aka the oldest layer of dirt or rock, right? The strata. The oldest strata, the oldest layer of material will always be so this bottom layer is the oldest, right? And then a little bit younger, a little bit younger, a little bit younger, right? Youngest. And so you should know that this layer, it should be younger than these bottom layers. Anyway, so I go to this bone. All right, I can now figure out about when did that animal die that produced that bone. Well, it's 83.9. Keep going. 83.7, probably as close as I'm gonna get. So that's a little bit less, which means it's actually a little bit younger than this many years. So I'm just gonna say 1,400 years. And I can check. Hey, I'm right on. Okay. Now, you can do the same. If you do come across one where the percentage drops down too low, you might need to go find a different isotope. Notice this stops carbon-12 at 10.9%. I'm at 0.8, so I'm going to need to use one of the custom isotopes here. Notice now I went into 50 or 75.8, so I can use that custom isotope for that. I might need to do the same for here, only this one might have to be a little older, or yeah. So now we have to use an even older one. So the fossils you're going to try to use carbon-14 or custom, and then rocks don't have carbon-14 in them, so you have to switch over to uranium. Okay, and yeah, this one will work with uranium. You'll always be able to tell if it's going to work if the percentage is something that's going to be manageable on this chart. So you're part of what I'm testing you guys on is, can you use this chart to estimate the age of these materials. I'll go ahead and do this one. Your job is going to be to complete the rest. Okay, so at this one, 82.3. So when you scroll up, 82 point, a little too far. 82. Nice. And 1.25 billion years. So 1.25 billion years. Oh, I didn't like that. Okay, is it really going to have me put 1.25 in billions? 5, and a billion would be, there's 1,000, million, billion. All right, every 3 zeros you're going to get hundreds, thousands, millions, billions, 1.2, right? Hey, oh man. Well, you're going to have to convert your years into actually, actual numbers. Right, but you can see it is all feasible. How will we know that you've done all of them correctly? Because there's going to be green, little tiny happy faces next to it. If it's red, that means you guessed wrong, and if there's nothing next to it, it means you didn't do your job in dating all of these. All right, so how are you going to submit this? When you're done with all of these, I want you to take your camera, like a cell phone camera, and I want you to take a selfie, with the screen. You might have to use a flash because I want to see both your face and the screen. And you're going to submit that, okay? So selfie with the screen showing all of your correct answers. All right. Hopefully you have fun with this. Shouldn't take too long. You will have to manipulate. Are you dealing with something live? Are you dealing with a rock, or you maybe need a custom time frame? Okay. All right. So enjoy this. Again, I will have the PhET simulation so you can do this. The website listed. So thank you. And good luck.